Right. Now let's briefly talk about what kind of structural system that we use for tall buildings, right? So this is one. So usually, if you're looking at system less than 60 meters, though we call here as a non-rigid frame, actually they are rigid, but it is in a relative sense. Okay, and we have small columns and girders, and this is called as a non-rigid frame. So though terminology given here is actually non-rigid compared to the other structural system that we are going to talk about, it is going to be non-rigid, but however they are all moment resting connection. So this kind of system, frame system, moment resting frame system, we can use it for buildings for height up to 60 meters. Of course, these frames, depending upon your lift core opening and stair wall openings, you can also put your shear walls. So that will also help. Then, if you make the columns really large and girders also make it large, and then with the connections, if you make it really stiff, then we can increase the height of the construction from 60 meters to 120 meters, right? So this is system is called as a rigid frame system. And the next system is, along with this rigid frame system, what you do is at each floor you also add these bracings. Okay, and these are called as, either you put again shear walls or X bracings. Okay, at each floor. The only thing is, if you are doing a building, if you start, you cannot have walls in the exterior. Let's say it is going to be an apartment building. Nobody wants to. Everybody wants to have an open space. They want to see the outside world. So you cannot block the space on the outside, right? So again, the same way, this bracings have to be designed in such a way that it is not going to obstruct the functionality of the particular building. Then this is your brace frame. You can brace frame along with this rigid frame. In fact, if you put brace frame, the dimensions of the columns and the girders can be actually optimized. Then again, frames, braced frames, along with your rigid frames. You can also, what we can create is something called as an outrigger trusses. Okay, so these, look at it, these certain locations. What we do is we develop a very stiff truss system, and put it at certain levels, and these are called as outrigger trusses. Okay, they're going to connect the outside perimeter frames along with the inside core that you may have. Okay, in this way you can get a very efficient structural system. You can increase the height from 180 meters to, in fact, to 250 meters, and with these kind of systems you can optimize the dimensions for your columns and girders. And usually these kind of outrigger trusses are put 15 to 20 stories apart, like what you're seeing here in this picture. Now, if you want to go for more taller structure, usually what we go for is basically tube system, okay, or it's called casting system. It is efficient from 280 meters to 360 meter, where you have large columns and girders like this. Basically, what you have really created is a perforated tube, like this kind of frames along all the perimeters, both at the exterior level and also at the interior level, and they can also be connected by outrigger system. So with these kind of systems, again, you can go for 280 to 360 meters. Now, what I can do is, so you know that the box section is actually having much more rigidity, right? From structural efficiency point of view, what we can create is, we can also create multiple number of these kind of tubes and arrange them together so that everything is going to act together. So, like again, I've told you, when you have two springs that are connected in parallel, now I can arrange the stiffnesses of these individual tubes in such a way that I can come up with a very efficient structural system. Okay, and this kind of system is efficient for 360 to 500 meters, and where in this system you're going to have large columns and girders, and usually you end up with a very heavy structure. Now, this is a new system which is in the recent, I would say, 20, 30 years. A lot of constructions are happening because of the improvement in the fabrication and construction with the invent of modern tools. So, what we have here is a diagrid system, along with these kind of perforated tube system, we can also create this kind of a diagrids which runs along several stories, okay, and all the four sides. So it's basically like a bracing, and it is also going to help in transferring the load, and you end up with a very efficient structural system. What we can do is with this kind of system, these bracings are going to relieve the loads on going to the columns and beams. Then you can optimize the size of the columns and girders, and in this way you can get a very efficient structural system. Usually these are used from 250 meters to 500 meters. And this is when you go more than 500 meters, you really going into very exotic structural designs. And there, in fact, the core system will be kept inside, and the core design would be much more heavy, and it will be very involved. In fact, this is the same buttress core system that was used in Burj Khalifa as well, and usually they are very efficient more than 500 meters. You're going to look at use large shear walls at multiple locations. In addition to that, you're also going to have this kind of a tube system along with the heavy cores that you're going to have. So with this kind of system, you can also have small float plates. You'll end up with small float plates. Right. So these are the evolution of systems. Nowadays, if you look at the structure that are built more than 600 meters or so, usually they have this buttress core systems with large shear walls. Okay. Now, what is it? So this is what we talked about, the rigid frame action. Say the columns and beams are all connected together rigidly, right? And the joint rotates by the 90-degree, right? So in this way, you get this frame action. Now, along with that, you also have shear wall. Shear walls, as I said, the inclined rigidity is going to be very high because your width of the wall is going to be quite large, right? And the moment of inertia, if the wall is going to bend like a cantilever, and we know that the moment of inertia will be large if your depth of the member is large, right? So in this way, again, we can resist a huge amount of lateral force by putting the shear walls. What I can also do here is I can connect both of them and make the system more efficient. Okay, so like this. So you can also connect the shear wall and frame to transfer the forces. Again, I said both of them are going to act together like two springs that are connected in parallel. Depending upon how we connect it, this is a parallel connection. So both of them are going to contribute to the stiffness. So you end up with more efficient structural performance. Now this is the tube action that we talked about. Basically now, instead of looking at one single wall or one single frame, now what I do is I connect these frames and make them as a tube. Okay. So again, the structural efficiency is going to be better if you have this kind of tube action. That is what it is relied upon, this bundled tube. Okay. Now several of these individual tubes are connected together to create a very stiff system. Okay. So in summary, usually up to 20 stories, only with moment resting frame we can do the construction. But however, the moment you go for 20 story and all, definitely you need elevators. So the lift core can be effectively utilized to construct the shear walls and connect them with the frame, right? And up to 50 stories, again, shear wall and frame, combine them, you can come up with a very good structural system. In fact, more than 80 stories, you start using this bundle tube concept, right? About when you're talking about 100-story building and all, then usually the modern day construction they adopt this buttressed core system for shear walls with large shear walls, right? And this is the system that we use. Okay, right. Now let's look at what are the popular reinforced concrete structures that are there around the world and in India. And as I've told you, this is a bundled tube system, right? And also we have the buttressed core. So it's a combination of a tube system plus buttressed core. And this buttressed core consists of a hexagonal core which is reinforced by three buttresses which is in the form of Y shape. Okay, and you can see this structure has 160 stories. Okay, and it is at about 830 meters tall. It's quite tall, right? And this is again one of the very famous iconic structure, which is a Petronas Tower in Kuala Lumpur in Malaysia. They have two 88 stories plus 5 basement towers, and they are about 379 meters tall. And again, the structural concept is tubular structure with shear walls and concrete frames. Okay, so along with concrete frame and shear wall combined together, and you create a tube, multiple tubes as well as with shear walls, is a system that they have adopted. And the external cladding is made with stainless steel and glass panels. Right. This is the structure that is there in our own country in India, which is called World One Towers in Mumbai. And three towers were actually originally proposed, and they have 76 stories plus two basements, and they stand at about 208. One of them is tall, which is about 285-meter tall. And actually, the original proposed height of the construction was 442 meters, but due to various reasons, they stopped at 285-meter tall. And the structural concept is again, you have multiple concrete frame, which are also connected to the core wall. Again, the external cladding is with stainless steel and glass panels. Right. Now, this is again some of the, I would say, very iconic structures which are around the world. And you see here, I think Bandra Orly ceiling, and it is made of pre-stressed concrete, again made using concrete as a material. And you can see here, its main span is cable stayed, and it is in very aggressive environment from corrosion point of view. And the next, if you the picture is the cantilever bridge construction, which is Shibanpo Yangtze Bridge from China, and you can see the main span is about 330 meters, right? And the another one is from Abu Dhabi in UAE, which is Sheikh Zayed Bridge, and again you will see a nice segmental concrete girder construction, and it actually the design resembles the sand dunes that are prevalent in the UAE region. And this is again, you can look at 298-meter long span. It looks very elegant. It's again constructed using this balanced cantilever construction method. And you can see, compared to the span, the thickness of these segments are very, very small right in the middle. Basically, you can see these kind of variety of shapes that you can make using concrete. The moment you create a formwork or using precast systems also, if you're able to do it, you can create this kind of iconic structures if you use concrete as the construction material. Right. So now we have looked at buildings. We looked at some examples of bridges. Again, concrete being very strong in compression. It is also heavily used for constructing dams. And this is one of the dam, which is called as Gordon Dam, which is in Australia, which was opened in 1978. What is the unique feature is this dam has a double curvature arch dam. Okay, and it is curved both in the vertical and horizontal directions, and it is designed in such a way that they can really resist very large hydraulic pressures, and it stands about 140 meters, and it has a length of about 198 meters. So again, subjected to water, you can see, always in contact with water. Again, even in India, we have built several dams using reinforced concrete, and Bakranangal Dam, which is in the border of Punjab and Himachal Pradesh. It was constructed in 1963. In fact, it is one of the highest gravity dam in India, and with a height of about 207 meters. It is also Asia's second tallest dam after Tehri Dam in Uttarakhand. Right. So far, we have discussed the history of RC and various structural systems and so on. Now, let's look at briefly what are the advantages of reinforced concrete. Okay, and as I've explained, reinforced concrete construction, concrete as a material, it has a very high compressive strength, and it has excellent resistance to fire and water. And of course, water, we have to be careful. We have to make sure that the concrete is not permeable. Okay, and also for the design load, we need to make sure that if it is a water retaining structure, you have to make sure that you design it for a specific crack width or crack free concrete. And RCC structures in general are they're very rigid. That is the reason if you look at it, the main structural system for tall buildings are all made of concrete. And if you design well, both at the material level as well as at the structural level, it can lead to very long service life. Again, durability is one of the main design considerations in the recent years. So we can really build a very long service life structures made of RCC, and it usually has low maintenance cost. Again, if it is done properly, and major advantage, as you can see here, formwork, if you are able to create, you can create a structure of very complex shapes like the one that you're seeing it in the picture here. You can see, you can really construct structures of very complex shape. And it is versatile and can be used for various structural components like footings, columns, beams, and slabs, etc. And it can be molded to desired form and shape. And one of the I consider one of the most advantageous aspect of concrete construction is you can make it using locally available materials in most of the areas, and also you don't need a very heavy technically skilled labor. Lower grade of skilled labor, if they are trained properly, they can be used for casting and steel fabrication, right? So these are some of the advantages of reinforcement in concrete construction. Right. Now, disadvantages, of course, any material will have advantages as well as disadvantages. So, depending upon the requirement, you have to choose a material, right? So, RCC again, we know that concrete has very good compressive strength but poor tensile strength. So, we have to design the reinforcement. If your tensile reinforcement is not designed properly, again, it can lead to brittle failures if you're not careful enough, and it can lead to cracking, and it can lead to serviceability issues and so on. Okay. And another important aspect is like this, this is one of the construction that we were associated with. A very large formwork is required. Forms are essential for concrete. In fact, for cast in place construction, the cost of the formwork can be 30 to 40% of the actual cost of the construction. It can constitute a very big part of the concrete construction. Again, for very long span structures, because concrete, you end up with massive sections. So RCC sections may become very heavy when compared to steel, right? So that is one of the disadvantage. Again, the way you do the quality control, right from the material level and at the construction level, it can have a very dominant effect how the structures are going to perform. So the quality control, both at the material level as well as at the structure level, when you're constructing as well as at the design, you have to be really, really careful. Again, concrete can shrink and can lead to a lot of shrinkage cracks if you're not designed properly, right? And creep. Again, concrete also can creep. We'll talk about creep in the coming module. Basically, creep is nothing but under constant stress, the strain is going to increase over a period of time. So that will lead to additional deflections and other stresses, which we'll talk about in the next coming modules. So these are we talked about advantages as well as the disadvantages. So as we have explained, concrete is strong in compression, steel is strong in tension. So basically, we make good properties of both these different materials and create a new structural material which is reinforcement concrete. One advantage with why the steel and concrete works very well is their thermal coefficient of expansion is nearly same. So, for example, for concrete, it varies from 0.000010 to for steel, it is 0.000012. So, nearly they are same. So, there are no residual stresses that are going to develop because even if it is a temperature effect, they're going to expand by more or less the same amount. So you end up with negligible internal stresses resulting from temperature changes. So that results in very good bond between these two materials. So that is why several structures are standing for more than 100 to 200 years, right? And steel, when used as a reinforcement, again it is susceptible to corrosion. We'll talk about in the module 3, where we'll talk about the durability aspects, what all the things that we need to consider, right? So steel is susceptible to corrosion, but however, if you design the concrete well and it can really protect the steel, and it can lead to better durability. Right. So now let's move on. What is the effect on the using this material from construction from environment point of view? As you all know, the sustainability has become a big important aspect, and everybody is talking about carbon neutrality and so on, right? So in terms of energy use in building, in fact, 36% of the total energy use, in fact, the building sector accounts for it, out of which 65% of them goes to electricity consumption. Again, the material that what we are using has to be in such a way that they are thermally very efficient. Again, that also we have to account for it. Again, the energy used in building accounts for 30% of greenhouse gas emissions, and it also accounts for 30% of raw materials use, and 30% is the waste output. It works out to be 136 million tons per year, and also it accounts for about 12% of total potable water consumption, so which is a huge component. And in terms of waste that is generated from construction, new construction accounts for about 8 percentage. And in fact, I've taken this information from this US Green Building Council. And when whatever that we're using for renovation, that accounts for about 44 percentage. And whatever the old structure that we're demolishing, that accounts for about 48%. So the building sector, the energy consumption accounts for major part of the total energy use. So as I've said, it is accounts for about almost 36% of total energy use. Let's compare embodied energy per stiffness. The embodied energy is basically is measured in terms of CO2 equivalent. How much CO2 equivalent per kg of the material is generated. Here in this slide, we are comparing different materials: wood, brick, concrete, steel, and aluminum. Right, and so what we are really here comparing is the specific the energy required per specific stiffness. What is specific stiffness? Specific stiffness is stiffness of that particular material divided by the density. Okay, so if you divide the stiffness by density, you get the specific stiffness. Then the energy you divide by the specific stiffness, you get the energy by stiffness. In fact, we should write specific stiffness. It's specific stiffness, energy by specific stiffness. So if you look at compare the different materials, right? So ideally, actually, if you look at it here, wood energy per specific stiffness is about 53, and for brick it is about energy required for specific stiffness of 168, and concrete is about 738, and steel is about 1597. And for aluminum, it is not a very energy efficient material that can be used for construction. But concrete, if you look at it, it's not too bad. It is about 738, better than steel and aluminum, right? So from this point of view, again, you can clearly say that concrete still with it can be efficiently used for building construction to reduce the energy aspects. Right. So now let's look at the how the cement and concrete plays a role on sustainability. And here, what we have is, in fact, cement production contributes about 8% of your global emissions. And this is a chart that's taken from this reference here. It basically projects millions tons of cement, that is in the y-axis, and in the x-axis it is showing how the cement production is increasing in different countries from 2010, and also it is projecting in 2050 how it will stand. Okay, so we have in each year we have considered two cases: low demand case, and then we have a high demand case, right? So if you look at it from 2020 point of view, let's look at the high demand case. So for example, the Indian consumption, if you look at it, it is in the orange color. So roughly we are looking at about 500 or so, right? 400 or 500 million tons of cement in 2020. And in fact, if you look at it, we are very behind China, right? And also we are slightly lesser than OECD countries. right? But if you look at in the year 2050 for a high demand case, in fact, India is going to overtake in terms of cement use and cement production compared to that of China. And India will become one of the largest producer of cement as well as for consuming it. Right. So this is again the data from India point of view, as we have explained in the previous slide. And in the y-axis, we have million tons of cement, and in the x-axis, different years. So you can see here in 2020, we are about for high demand case, we are about 500 million tons is what is being has been produced in India in 2020 as per the statistics. Right. In 2050, you can clearly see here that the production is going to go from 500 tons to almost 1300 tons or so, right? So, again, India is the second largest producer of cement in the world. One of the most, in fact, our plant have become more efficient, and it is one of the most energy efficient as well. And demand for cement and concrete is very enormous in India. And cement production at 337 million tons in 2018-19, it can reach by 1000 million tons by, as we've seen, by 2050 per year, right? So there's a huge demand for cement and concrete. So we, in fact, 1 ton of cement production leads to closely about 1 ton of CO2 emission. Again, we have to be very careful. Our production process also should become more energy efficient, right? Now, in terms of future of cement and concrete construction, of course, the raw materials are very abundant in India, and it leads to lower embodied carbon footprint and embodied energy than other materials that are available for construction. And now with the research, people also develop alternate binders like geopolymer concrete and all it is available. And we have also gone for more high performance concretes with very high strength, and ultra high performance concrete with very good durability are more and more available, and people are also more and more adopting in various constructions, so that can lead to more sustainable and durable solutions. And again, durability should be considered in initial design. So if you can make the structure to last longer, then again you are reducing the carbon footprint, right? So we have to make sure that we design the structure to last forever. Okay, and reductions in CO2 emissions during cement production is also a need. We have to make the cement production more and more efficient, and we need to reduce this CO2 emissions during the production process. And we should also encourage recycling of concrete. Now, a lot of plants, recycling plants are also being established in several cities in India. So, concrete, the used concrete can be broken up and cleaned and can be used as a recycled aggregate. And that is going to produce, promote the circular economy instead of a linear economy. And again, we can also reduce the use of water using modern admixtures. Okay, so this is again the figure that explains how this recycling process. So construction demolition waste, what we can do is we can crush them and we can make them as a recycled aggregate and powder that can be used as a fine aggregate. Again, we can make recycled aggregate and so on. So this process can be made closed loop, and so that we don't waste the material. Right. So to conclude for this first module, what we have discussed is the evolution of concrete and reinforced concrete in general. We started talking about how the concrete evolved, right? From 1800, John Smeaton, the UK British engineer, first he explored using this burning limestone and clay together. But Joseph Aspidin was the one who actually patented and invented this Portland cement, which is what we are in modern day construction we have been using it. And then Joseph Monnier, French florist, he invented the concept of reinforcing the concrete while making flower pots. So he added wires to make sure that the tension. And then Hennebeck system we discussed, right, where even the modern building reconstruction will use longitudinal bar and stirrups. That was also discussed. And then we talked about latest innovations like ultra high performance concrete also. And again, we talked about different structural systems and how the load path happens in buildings, right? And also in tall buildings, how various structural systems are adopted in a nutshell, in a very concise way we discussed. And we also talked about advantages and disadvantages of reinforcement concrete construction. and we also talked about influence of cement production on sustainability aspects, which is very very important again, and also future of cement and concrete construction in India and abroad was presented. Right. So with this, these are some of the references. I think you can look at it. I think some images were taken from the internet, and the references have been given here. And so with this, we will end the module one, and we'll meet again for the second part of this first module. Thank you.